In this tutorial, we'll cover the independent samples t-test. I recommend you follow along in the Student Study Guide with IBM SPSS Workbook. The independent samples t-test is used when you have two independent groups and you want to compare the mean scores for each of these groups. So that means that your second variable needs to be interval or ratio. Here we have an experimental condition of gesturing, and participants were assigned to either not have any gesturing or to be in the gesturing group. The creativity variable is the number of novel feasible uses identified for an object, and this is a ratio variable. The data are provided on page 172 of the workbook. You might want to enter that data and follow along. Click pause if you want to do that. To calculate an independent samples t-test, go to the menu bar, click Analyze, Compare Means, Independent Samples t-test. Next, we identify our grouping variable and our test variable. The grouping variable is an IV in an experiment or the group predictor variable in a non-experimental study. So I'm going to put my experimental condition to my grouping variable, and then I need to define the groups. This is based on how the groups were coded in your data set. The numbers that you enter here need to match your data. I'm going to enter 0 because gesturing was coded as 0 and 1. Click Continue, and then I send creativity, my DV, to the test variables box. Then I click OK. Then we get our output. The first table shows the descriptive statistics for each of our groups. In this case, the no gesturing group had a mean of 6.25 and a standard deviation of 1.55 rounded. The gesturing group had a mean of 8.08 and a standard deviation of 1.93 when we round. The next table shows the results for our independent samples t-test. Independent samples t-tests are a little bit complicated to interpret at first. I recommend you follow along on pages 174 to 175 of the workbook. The first step is to determine if we violated the assumption of equal variances. The Levine's test is what tells us whether or not we violated our assumption. We're actually looking for a p greater than 0.05 because that would tell us that our variances are about the same or that we can assume equal variances. In other words, that our standard deviations for each of our groups are about equal. And here we see that the p-value for Levine's test is over 0.05, and that means that we can assume equal variances. That simply means that when we're interpreting our t-test, which is the whole reason we did this analysis, we can look at the first line. In other words, we don't need to make any adjustments because we've met our assumption of equal variances. Now, once you make that decision in terms of which line to look at in your output, you don't ever need to think about the Levine's test again for this output. And now you can focus on the results of the t-test itself. Here we see that our t-value is negative 2.57, degrees of freedom 22, and our p-value is 0.017 or 0.02 rounded. Is that a statistically significant difference? If you said yes, you are correct. This tells us that there is a statistically significant difference between our no gesturing and our gesturing groups. When we look back at the descriptive statistics in the first table, we see that those assigned to the gesturing group had a higher creativity score than those assigned to the no gesturing group. After calculating your independent samples t-test, you'll also want to calculate an effect size. Unfortunately, there's not a super easy way to do this in SPSS. You have two options. One, you can do in SPSS, and that's to calculate a point biserial correlation. You go to Analyze, Correlate, Bivariate, and then you send both your variables over. Pearson will be checked even though this is a point biserial correlation, and then you'll click OK. That will give you your point biserial correlation. To find the proportion of variance accounted for, you need to square that number. Take, in this example, 0.4 0.481 times 0.481 equals 0.23. That is your point biserial correlation. In other words, 23% of the variance in creativity is accounted for by our experimental condition. The other option is to calculate Cohen's d, which is a standardized difference score. You can calculate this by hand, but I'm going to show you here how to use an effect size calculator developed by Dr. Lee Becker at University of Colorado at Colorado Springs. So thank you, Dr. Becker, for creating this online calculator. Take your output and enter the information into the calculator. So here we're going to enter our mean of our first group. It doesn't really matter which group is which, our mean of our second group, our standard deviation for our first group, and I'm going to enter it to all the numbers so that I get the most accurate results, and then I'm going to click compute. And here you see we get our Cohen's d of negative 1.05 when we round. That's what we would report in our results section. The reason it's negative is based on how our data were coded. If we had entered the means differently, so if we had called 6.25 the mean for group 2 instead of group 1, we would have gotten a positive instead of a negative number. You can also calculate a point biserial correlation this way, although remember you'll need to square this number in order to get the proportion of variance accounted for. That's the end of this tutorial. If you need additional help with calculating and interpreting independent samples t-tests, go to the SPSS tutorial on this subject.